Hello everyone. In this very video we are going to be looking at viscosity and the calculations involving viscosity, the Stokes law. Now viscosity is the measure of fluid's resistance to flow. I like to also use the word viscosity is friction in liquid. So when you say a liquid is a viscous liquid, it means that it drags, it does not flow easily. A good example of a viscous liquid, we have oils, we have gels, and so on and so forth. Now, when you put a sphere in a viscous liquid, let's assume this is a viscous liquid. Now, that sphere experiences three forces. There are three forces acting on this sphere. The first, like we see here, is the weight, which tends to pull the sphere downwards, because when you put a sphere in a liquid, it will definitely move downward. So, and that's the weight. Now, but if you notice, there are two upward forces that act on the sphere. One of them is upthrust, which acts in every liquid. Every liquid experiences an upthrust force. Now, but there is a second upward force too that resists the movement, the downward movement of the sphere, and that is viscous force, which we can also call the drag force. It opposes motion. Remember, when we studied friction, friction opposes motion. Okay, so we have this. These are the three forces. Now, upthrust, what is the formula for upthrust? Upthrust is the density of liquid. Upthrust in a liquid is the density of the liquid times the volume of the solid immersed times acceleration due to gravity. That is one definition for upthrust. Density of liquid times volume of solid that is immersed times acceleration due to gravity. Now we can say that the volume of solid immersed, here we use a sphere, and the volume of a sphere is 4/3 by r cubed. Then the density of the liquid, which is rho L, then acceleration due to gravity. Okay. Now the weight of the sphere, weight we know is mass times acceleration due to gravity. Now, but mass is the same thing as density times volume, so that shouldn't surprise you. Mass is density times volume, so we can say that the weight of the sphere is density of the sphere times the volume of the sphere times acceleration due to gravity. The volume of the sphere is the same thing like we have here, 4/3 pi r cubed. That's the formula for volume of a sphere. Then we have the density of solid and acceleration due to gravity. Then the viscous force has a formula according to Stokes' law. Stokes actually discovered that viscous force relates with velocity, terminal velocity, and viscosity according to this formula. And so our viscous force is 6 pi r rho v naught. Now your rho here stands for coefficient of viscosity. Every liquid has a coefficient of viscosity. Then your V naught here stands for terminal velocity. Let me pause and say something about terminal velocity. Terminal velocity is that constant velocity that an object possesses when it is moving down a viscous liquid. Now, when an object is dropping down a viscous liquid, the velocity keeps increasing, but it gets to a point where the velocity becomes constant. At that point, that object is said to attain terminal velocity, which we denote as V naught. Okay, so if we follow the resolution of forces based on what we have in the diagram here, you can see that W minus U minus V equal to MA. That's according to Newton's second law of motion, that states that the resultant force acting on a body is equal to the product of its mass and its acceleration. Okay, so the resultant force W is going downwards, U and V are moving upwards, so opposite direction. That's the reason for the subtraction. Don't forget that when two forces are moving in the same direction, the resultant force is to add the two forces. But when they are moving in opposite direction, the resultant force is to subtract. So that's the reason for the subtraction here. Now, at terminal velocity, remember, terminal velocity is that constant velocity. Acceleration is zero, because whenever velocity is constant, whenever velocity is uniform, acceleration is always zero. Okay, so this MA now, our formula MA here reduces to zero because acceleration is zero. And we can now say that the weight W is equal to U plus V, making W the subject of the formula. Okay, so this formula is only possible at terminal velocity. So this is the formula at terminal velocity. Now, if we substitute the values for this, for the weight is 4 over 3 pi r cube rho sg, equal to, for upthrust is 4 over 3 pi r cube rho l g. Then plus for viscosity, it is 6 pi r this, then v naught. Now this is exactly what we get, which you can have 4 over 3 pi r cube rho sg minus 4 over 3 pi r cube rho lg equal to 6 pi r rho v naught. Okay, good. Now if you look at here, there is a like term which is 4 over 3 pi r cube g is common to both of them, and what do we have? We have rho s minus rho l equal to 6 pi r rho v naught. Now if we make the coefficient of viscosity the subject of formula now, it is going to be 4 over 3 pi r cube g rho s minus rho l all over 6 pi r then v naught, which at the end of the day is going to give us 2gr squared rho s minus rho l all over 9v naught. So we can say that the coefficient of viscosity is equal to 2gr squared into rho s minus rho l all over 9v naught. So look at the first question here. The terminal velocity attained by aluminium sphere of radius 1 millimeter falling through water at 20 degrees Celsius is, okay, we are given the density of aluminium to be 2,700 kilogram per meter cube, density of water to be 1,000 kilogram per meter cube, coefficient of viscosity to be of water is 8 times 10 to the power minus 4 poise, or you can say Pascal second. The unit of this can also be Pascal second. Okay, so let's see the solution to this very problem. From the question, we are given that the radius of the sphere is 1 millimeter. 1 millimeter is the same thing as 0.001 meters. You achieve that by dividing by 1000. So to convert millimeter to meters, you divide by 1000. The density of solid, which is the aluminium, is 2700. The density of water is 1000. And the coefficient of viscosity is this. So we are asked to find the terminal velocity. Now, from our formula from Stokes' law, we see that V naught is equal to 2gr squared into density of solid minus density of liquid all over 9 times viscosity. Now these two can interchange. So meaning that if I'm looking for viscosity, it means here will be 9v naught. That 9 times the terminal velocity. But in this question, we are looking for terminal velocity, so we are going to have this. Now if we substitute the values correctly, this is going to be 2 times your g is 10 times your radius is 0.001 squared, then into the density of solid is 2700 minus the density of liquid of the water is 1000. Now all over 9 times viscosity, coefficient of viscosity, which is 8 times 10 to the power minus 4. If you use your calculator to do this, you're going to get 4.72 meter per second. So the terminal velocity is 4.72 meter per second. Now let's see another question here. The terminal velocity of copper ball of radius 2 millimeter falling through a tank of oil is 6.5 centimeter per second. Compute the viscosity of the oil if density of oil is 1.5 times 10 to the power 3 kilogram per meter cube and density of copper is 8.9 times 10 to the power 3 kilogram per meter cube. Now let's write out the quantities here, the values. The radius we are given, the radius of the copper ball is 2 millimeter. When you divide by 1000, you get 0.002 meters. Terminal velocity is 6.5 centimeter per second. Centimeter is not SI unit, so to convert to meter per second, centimeter to meter, you divide by 100. Okay, so that's why we have 0.065 meter per second. Then we are given the density of the liquid, which is the oil, is 1500, and the density of solid is 8900. And in this case, we are looking for the coefficient of viscosity, which we've written to be 2gr squared. We have rho s minus rho l all over 9 times terminal velocity. Remember, I told you that these two can interchange by cross multiplication. So if we substitute values, this is going to be 2 times 10 times your r here is 0.002, and your density of solid 8900 minus density of liquid 1500 divided by 9 times the coefficient of viscosity, the terminal velocity is 0.065. okay, so if you compute this with your calculator, you're going to get 1.012 Pascal seconds. Okay, now we see one more question here. The third question here, we are given that a sphere of radius 1 millimeter falls through a viscous liquid with a velocity of 10 meters per second. If the coefficient of viscosity of the liquid is 0.15 poise, poise, also Pascal second, what is the drag force? In this case, we are looking for drag force. Now, but the radius of the sphere is 1 millimeter, which is 0.001 meters. The coefficient, the terminal velocity is 10 meters per second. And while the coefficient of viscosity is 0.15 poise or Pascal seconds, okay? Now, what is our formula for drag force? We say drag force is 6 pi radius, coefficient of viscosity times terminal velocity. I think it's a straight forward formula. So this is 6 times, this is 3.14 times my radius. Our radius here is 0.001 times the coefficient of viscosity here is 0.15. Then multiply by the terminal velocity is 10. So if you use your calculator to compute this, you're going to get 0.00283 newtons, which we can still write as 2.83 times 10 to the power minus 3 newtons.